This video is a discussion of density and some conversions between the three different temperature units. So density, let's start off with that. All right, so the definition for that is a ratio of a matter's mass to its volume. It's a great definition, but really the way I like to think about it is how tightly packed is something? Are the atoms and molecules really tightly packed? If they are, then that substance is dense. If they are not tightly packed, then that substance is not dense. And those molecules and atoms are farther apart from each other. So if you look on your periodic table, you can see gold has a density of about 19 grams. So the way that the unit usually works is grams, which is the mass unit, divided by milliliters or centimeters cubed, which is the volume unit. And so I've got a cube that is a centimeter by a centimeter by a centimeter on each of these sides. So this would be like a really small playing dice. And so that really small playing dice, if that thing was solid gold, that mass would be 19 grams. That's a lot. Iron's mass is less than 8. Copper's is less than 9. Lithium's is a 0.53, 0.54, something like that. So that's very not dense, which is why your phone doesn't weigh a whole bunch, because it's got a metal battery inside of it. The metal that it's using has got a very low density. Okay, so my analogy for this is my sister moved in with me when she was 12. And we would take some trips. I bought identical bags for us, these duffel bag things, and I would have to come in and forcibly shove stuff into her bag to get it to zipper down. Didn't need to do that with mine. The bags were identical, except hers was always much more dense than mine because she forced me to pack as much into it as possible. The equation is density is equal to mass divided by volume. So there we go, a ratio, which this is a ratio of a matter's mass to a matter's volume. Awesome. So we're not going to use the equation in this class. We know what it is, and that's fine. We're going to use the units to calculate out how we're going to figure out density of an object. So we'll just make something up. Let's say that I've got an object and its mass is 278 grams. And this, whatever this object is, it has a density of 4.2 grams per milliliter. And my question is, how many milliliters, how big is this object? What is this object's volume? All right, so I need an answer that has milliliters in it. So what I'm going to do is I'm going to start with 1 milliliter divided by 4.2 grams. So all I did is I turned this upside down, which is totally fine, because this substance, if I had 4.2 grams, it would have a volume of 1 milliliter. If I had 1 milliliter, it'd have a mass of 4.2 grams. So in the same way that 12 inches is 1 foot and 1 foot is 12 inches, it doesn't matter which one you put on top, because it's a definition. The top and the bottom are equal to each other. So for this substance, the top and the bottom are equal to each other. And so what we're going to do is I wrote it like this. So when I'm finished, I'm going to get a milliliter unit. So now I'm going to take the other number that I've got, which is 278 grams. And I'm doing that because I can cancel grams out with grams. The only unit that hasn't been canceled is milliliters. And let me grab my calculator. So this is just going to be 278 divided by 4.2. And so this is going to have this. So in my calculator, I got 66.191 milliliters. I only have 2 sig figs from my measurements. And so then the answer for this is going to be 66 milliliters with proper significant figures. Okay. That's it for density calculations. There's a whole bunch of them in the book. We've got worksheets if you want to work on those. A little bit more with this. You might see a lowercase d used as the symbol. You might see an uppercase d. You might see this Greek letter rho, which kind of looks like a lowercase cursive-y kind of p. It's the again, the lowercase Greek letter rho. Other things to know is water's density is 1 gram per milliliter. And things with different densities will set themselves up, float on top of each other, depending on what their densities are. So why does a balloon float, a helium balloon float in atmosphere? Because its density is less than that of air, so it floats up. Why is carbon monoxide dangerous? Because its density is higher than that of air. And so the reason the carbon monoxide monitors are placed on the ground or as low to the ground as possible is because that's where the carbon monoxide in a room is going to start. It's going to start filling from the bottom. So maybe filling up with a gas isn't super obvious, but if you had some water and you dumped in some salt water, the salt water would go straight to the bottom and then fill the container up from the bottom up. And so that's what carbon monoxide would do. It would fill the room from the bottom up. So anybody on the sleeping low to the ground, laying low to the ground would be affected before anybody standing. All right, so if anything that's got a density greater than 1 gram per milliliter is going to sink in water. Anything with a density of less than 0.1 or less than 1 gram per milliliter is going to float. So here's my question. You guys know that if you watch the intro video that I was on aircraft carrier, and the aircraft carrier is made of steel, and steel's density is about 7.7 grams per milliliter. Water's 1 gram per milliliter. How can an aircraft carrier float? The aircraft carrier floats because it's not just a chunk of steel. It's got a bunch of air pockets inside of it. So the reason that boats float is because they're mostly air. There's a little bit of stuff. Let me show you a couple of pictures here. So on the left, we've got the Titanic. And just for the heck of it, I looked up what the length of the Titanic was, and it's 883 feet. My aircraft carrier was 1,093 feet. So they're not that far off from each other, a couple hundred feet-ish. Obviously, this one sunk and this one hasn't sunk. So why was it that this ship sunk? It hit an iceberg. Okay, well, if this hit an iceberg, would it sink? And the answer to that would be no. And the reason is because the inside of the aircraft carrier looks like this. What you should be noticing is all of these red lines, vertical and horizontal lines. This ship is basically a bunch of small air pockets cut off by walls and airtight doors. So what you have here is a bunch of pockets of air instead of a bunch of air. Like a rowboat is just a big thing of air, and if you start putting water in it, it all leaves. But if the rowboat was filled with a bunch of different, basically balls or containers, and one of them got punctured, the rowboat wouldn't sink. So that's not what is going. If this aircraft carrier were to run into an iceberg and cut a hole in the hull, maybe these spaces here might fill up with water as much as was damaged from the outside, but the rest of the boat, all of this stuff, that'd be filled with air. And so the density of this ship is less than 1 and would stay less than 1 because I replaced some of the air with water, but not enough of the air with water to cause it to sink. So let's talk about the Titanic. So the Titanic runs into this iceberg. I'll use blue. Okay, great. Runs into the iceberg and it cuts a hole in the boat. So great, there's a big hole here. Water comes gushing in. And so what ends up happening is, I'll use this yellow. I didn't draw this, I drew it poorly, but I drew it with intention. So in the engineering space, there was a ceiling. So this is supposed to be the ceiling to the engineering space. And they had watertight walls. The problem is the watertight walls didn't go all the way to the ceiling. So when this space right here filled up with water, it went over the top of the wall and filled up the next space, went over the top of the wall, filled up the next space. And then these spaces just kept filling up. And every time I fill up one of these spaces, I push out a bunch of air and I put in a bunch of water. And the difference in density is about 1,000. So air is about 1,000 times less dense than water. If I keep filling these things up, it's sort of like filling up an ice cube tray by only putting water in the first ice cube slot. I just keep filling it up, adding water, and eventually it will all fill up. So I had enough water in this thing that this boat tipped forward and then snapped itself off because it was, never meant to support its own weight across its keel. So if they would have just finished off those walls to the top, we would never have had to have seen that movie. Alrighty. And I'm going to talk a little bit about temperature conversion. So we're familiar with Fahrenheit, probably a little familiar with Celsius, and probably not so familiar with Kelvin. All right, so the Fahrenheit scale, just using a few countries, the rest of the world uses the Celsius scale. Some numbers that I want you to know are 32 degrees Fahrenheit. You probably know that that's the freezing point, and 212 degrees Fahrenheit, that's the boiling point. In Celsius, I want you to know 0 degrees Fahrenheit is the freezing point, and 100, sorry, I don't know why I wrote Fahrenheit. 0 degrees Celsius is freezing, and 100 degrees Celsius is the boiling point. And if I'm going to talk about the Kelvin scale, I just add 273 to that. So 273 K is freezing, and 373 K is the boiling point. So freezing point, boiling point. Other numbers that I want you to recognize. I'll write this again. Fahrenheit and Celsius down here. And this is room and body. So room temperature, I don't know, we'll put down 70 degrees Fahrenheit, and body temperature is 98.6 degrees Fahrenheit. For room temperature for Celsius, it's about 22 degrees Celsius, and for the body, it's 37 degrees Celsius. So when you're doing a calculation, you should have these numbers in mind. And so if your calculation doesn't make any sense because it's way, way far away from 37 degrees, then maybe you did something wrong with your math. So those are the important numbers. How do I do the conversion? Well, if I've got my Fahrenheit, I have to subtract off 32 and then multiply by 5/9. Why 5/9? Because the Fahrenheit number is a smaller unit than the Celsius number. And so it's going to take more Fahrenheits to equal a Celsius. So you can see that the difference between these is 100, and the difference between this is 180. So if I go up 1 degree Celsius, I've gone up 1.8 degrees Fahrenheit. Okay, so it's important that there are parentheses here, because if you don't put the parentheses in here, then you're going to have 32 times 5 divided by 9. Then it's just going to subtract off the temperature Fahrenheit, and it's going to be wrong. Order of operations in your calculator. So if I've got the Celsius temperature, I can go Celsius temperature times 9 divided by 5 plus 32, and I can get to degrees Fahrenheit. So let's use one of these examples over here. So I'll go with 37 degrees Celsius times 9 divided by 5 plus 32. I'll type that in the calculator. 37 times 9 divided by 5 is 32. And imagine that, it's 98.6 degrees Fahrenheit. Great, so our unit conversion works because I got the same number. What you should notice about the calculation or the conversion from Celsius to Kelvin is there's just a subtraction or addition. And that's because the Celsius unit and the Kelvin unit are exactly the same size. So if you go up 1 degree Kelvin, you also went up 1 degree Celsius. So they're only offset by a number. And the reason they did that is nobody wants to hear that it's 295 K outside. That's not super helpful. They want to know minus 273, it's 22 degrees Celsius. So they basically redid this so it was 0 and 100, so they didn't have to say 273 and 373. Something interesting about the Fahrenheit unit is, so why is 32 degrees Fahrenheit the freezing point? Doesn't make any sense. Why 0 makes sense for the freezing point? So the significance of 0 degrees Fahrenheit is about salt. Salt in water, so salty water. All right, so the way this worked was Fahrenheit had a thermometer, and he put it in some water, and he froze the water, and he marked the thermometer. Then he added some salt to the water, and the water liquefied. Okay. And so then he got it colder, and then the temperature dropped. And so then he added more salt, and it liquefied. And he got it colder, and it solidified. And he added more salt, and it liquefied. And he got it colder, and it solidified. And he kept doing this again and again until he hit a value where it didn't matter how much salt he put in, it would not liquefy. And this is 0 Fahrenheit. So if it's 0 degrees Fahrenheit, throwing ice melt out onto your driveway will do nothing. 0 or less Fahrenheit is the point where brine water or ice melt or salt, whatever you're putting on there, can't do anything to it. So after we've crossed the 0 Fahrenheit, ice is pretty much not slippery. It's super sticky. If you take Chem 122, we'll talk about that a lot more. And that's it. That's all I got for this video. Thanks.